Additively separable utility functions are structured as the sum of individual utility functions for each good, expressed as u1 of x1 plus u2 of x2, and so on, up to un of xn. This structure imposes significant restrictions on the cross derivatives of the utility function, reducing the degrees of freedom in demand modeling. Specifically, it reduces the degrees of freedom to 2 times n minus 1, making the number of parameters grow linearly with the number of goods rather than quadratically. This linear growth is particularly advantageous in macroeconomic and financial contexts where the number of goods, or states of nature, is large. The The Frisch demand system is particularly useful when analyzing additively separable models. Here, each good's demand function is expressed as x sub I superscript f of lambda times p sub I, where lambda is the Lagrange multiplier on the consumer's budget constraint in the Marshallian system. This follows from the first-order conditions of the Marshallian system, where the marginal utility of each good divided by its price equals lambda. As a result, the Frisch demand functions are decreasing, and all goods in the additively separable model are normal, meaning they have positive income elasticities. In this framework, cross-price effects are mediated through the Lagrange multiplier, meaning that a price change for one good affects the demand for other goods similarly. The elasticity of the Hicksian demand for good I with respect to the price of good J is the product of good J's marginal share and the magnitude of the elasticity of x sub I superscript f. This product is positive but close to zero if the price change is for a good with a small marginal budget share. Good I's own price elasticity is the product of 1 minus its marginal share and the elasticity of x sub j superscript f. Even without functional form assumptions, the partial elasticity of substitution between good I and J can be a useful way to represent their cross-price effects. The elasticity can be defined as a ratio. The numerator is the corresponding Hicksian cross-price elasticity. The denominator is the marginal share of the good with the price change. In the additively separable case, the partial elasticity of substitution is positive and equal to the product of the two corresponding Frisch demand elasticities divided by the share-weighted average of all n Frisch elasticities. The additively separable model's parameters can be specified with n-1 marginal shares and n own price elasticities. These parameters are sufficient to determine all cross-substitution terms, income elasticities, and average shares. Alternatively, n-1 average shares, n-1 positive income elasticities, and 1 own price elasticity can determine all other elements of the substitution matrix. Additive separability also links the magnitudes of income and substitution effects. The income elasticity of each good is the ratio of its Frisch own price elasticity to the share-weighted average of all Frisch own price elasticities. This means that two goods with the same income elasticity must have the same Frisch own price elasticities, differing in Hicksian own price elasticities only due to different budget shares. In macroeconomic and finance applications, it is often assumed that the subutility functions are equivalent up to multiplicative constants, which can eliminate additional degrees of freedom. In the intertemporal case, these constants often take the form of exponential discounting, further reducing degrees of freedom. If all goods in the additively separable model have the same income elasticity, preferences must be homothetic, and the subutility functions must have the same constant elasticity. This is known as constant elasticity of substitution, or CES preferences, with Cobb-Douglas as a special case. In summary, additively separable utility ties cross-price effects to own price effects and links income and substitution effects in a structured manner.